Last week we saw in more abstract level, theoretical level, how we can find the parameters for artificial neural networks using vector propagation. And today we're going to look at that in more detail. First, by looking at the kind of operations that we need to do, and then look at how to do this with TensorFlow. So in this first part, I'm going to start with a brief revision of operations with matrices, with arrays, so a bit look on algebra. And then we're going to consider the computational graph and automated differentiation, which is what TensorFlow uses. And we're going to see how to use this to train with stochastic gradient descent, which will be the approach that we'll be using to find the best parameters. Okay, so a brief overview of the concepts here. You already dealt with the scalars and vectors and matrices and so on. We can consider this tensor, the concept here is more general, it's a relation between these objects. So you can imagine a tensor to be an n-dimensional array. It can have more than 2 dimensions, any dimension that you need. For our purposes here, we're going to consider all of these tensors because they will be objects in TensorFlow. They can even be just a single number. So that basically will be what is going around in TensorFlow, and that's where the name comes from. If we are dealing with matrices or vectors and tensors of any size, we can do subtraction or addition easily as long as they have the same size. So the idea here is very intuitive. You just apply the operation between the corresponding elements. So the sum of these two tensors will be this tensor, where this element is added to this one, and so on. So sum and subtraction are very simple. Multiplication, when you do matrix multiplication in 2 dimensions, it's a bit more complex, but if you recall this from algebra, basically we are multiplying these 2 matrices and we use the row of the first one with the column of the second one. So the number of columns in the first one must be the same as the number of rows in the second one. And the result in the product matrix for that row and that column is the sum of the products between all of these elements. So the first one on this first row with the first one on this column, we multiply, and then we add the product of the second, and we do this over all the columns and then all the rows until we fill the product matrix. So this is how we do matrix multiplication, and this is very convenient because if you recall from what the model of the neuron is like, we have precisely this kind of operation over all the neurons. So we need to multiply these numbers, add everything together, and this gives us this net value that then goes into the activation function. So if we represent weights and examples as matrices, a simple matrix multiplication can allow us to compute this value for all the neurons that we have represented and all the examples that we have in the input matrix. Since matrix multiplication is a very common operation and it's very efficiently implemented in the hardware, say GPUs, things like that, then this at the basis of neural networks makes the whole thing very efficient. We can also use in TensorFlow broadcasting like you did with NumPy. So this is a different type of operation. It's not the usual algebra matrix multiplication, but you can do element-wise operations and broadcast them as long as the last dimension or the last dimensions match between the 2 tensors. So if the number of elements in this vector is the same as the number of columns in this matrix, then you can, for example, multiply the 2 of them or add them or whatever operation you do, and it will be done element by element on the first row and then repeat it on the second row and so forth. So you can also use tensors for broadcasting just like arrays in NumPy. And you can combine these two. So this works well in batches and these kinds of combinations. For example, Let's suppose we create a tensor here that has two matrices of 2 by 3. And we have another one that has two matrices of 3 by 2. So these are stacks of two-dimensional matrices. And we can do a matrix multiplication between these matrices with this shape. And when we do this, the matrix multiplication from algebra, which works on two-dimensional matrices, what TensorFlow will do is apply this element by element over the whole stack of matrices. So basically, deep down in TensorFlow, we have these elemental operations that can be used to perform this kind of operations over tensors, over arrays of values that we have. Now, this is important mostly for understanding how TensorFlow works. In practice, when we start using the higher level APIs, we generally don't worry about these details, because then we use layers and so on, the classes that are already implemented, and that are hiding all these complexities. However, this is useful to understand, because not only so that this doesn't look like magic, how things work, but also it may happen that you may need to implement something yourself at a lower level, say a new kind of operation, a loss function, some regularization term, something like that. And in that case, it's useful to know how things work below the API that we're going to use. So we're going to start by doing simple networks using TensorFlow. When we move on to more complicated architectures or deeper networks, larger, we're going to use Keras. But it's important for you to remember that you have always the possibility of going to the bottom layer, which uses these operations to implement everything. So let's start with the basic example. Suppose we have this data set that I generally use for examples, and we have this very minimalistic neuron here that has the output with a sigmoid activation. It just has two parameters that multiply the values of the inputs, and the two inputs are the coordinates of each of these points. So each of these points has a pair of values that determines where it lies, and we output here with the sigmoid activation the probability of belonging to one of the classes. The other class would be 1 minus that probability. So we can draw a line at the 50% or 0.5 probability and separate the two classes. Now we can create a column matrix, this matrix with one column and two rows, with the weights of our neuron, and a matrix that contains our examples in rows. Each example is in a row, and we have the two columns corresponding to the two coordinates where the points lie. If we want to compute this net sum here, which is the sum of the products of each weight by the corresponding parameter for all the examples that represent the net, remember that we usually train the net in batches. We're going to see this in a bit more detail, but we can present a set of examples to our network by doing this matrix multiplication. Because we're going to obtain a matrix with one column and as many rows as the examples we have. And in each of these cells, we have the product of the first feature by the first weight plus the product of the second feature by the second weight. So with matrix multiplication, we can immediately get the net value in our neuron for all of the examples in that matrix. Then, if we apply the activation function to this matrix here, we get the output of the neuron for all the examples that we are presenting. So this is an example of how you can easily implement a layer of a neural network using matrices. Note that if we had more than one neuron, we could easily put here more columns, and this would work all the same. We would have in different columns the outputs of the different neurons, and it would be a matrix analogous to that one, only it would give us the output of the layer instead of the features of the points. Okay, so now let's see how we can apply backpropagation to this to compute the weights. We saw that what we need to do to update any particular weight is to compute the derivative of the loss function of the error with respect to that particular weight. This will give us the direction in which we must change the weight, and if we multiply that by some learning rate and go on the negative direction, so downwards on the slope of the loss function, we can update the weight slightly and reduce the error iteratively. As we are going through the network to deeper and deeper layers, we need to keep chaining these derivatives. So actually, backpropagation is an example, if we automate this, is an example of reverse mode automatic differentiation. And this is what TensorFlow implements. So basically, what we do is we pass once forward through all these computations so that we can have all the intermediate values, and we know how each variable is connected to the final value of the function. And then we can go backwards through the computation graph to chain together all of these derivatives. There are different ways of trying to compute the derivatives. Of course, one of them would be symbolic differentiation, where we compute the formula for the derivatives. We saw this last week, for example, here in the case of the quadratic error function and the sigmoid activation and so on, and I showed what were the equations for the derivatives. We multiply everything and we get an expression. However, this is not very practical to generalize, so if you build your own network arbitrarily, then having to do symbolic differentiation to obtain the final expression could be very hard, and it would be especially difficult if you use conditions or loops or something like that inside your network. So in that case, it could be very hard to obtain this expression. An alternative would be to use numerical differentiation. We make small changes to the values and see how things change, and that way we can estimate the derivatives of the function. However, this is very inefficient computationally. You need to do lots of different steps, and it may have problems with the convergence, stability, and so on. So what we use for training neural networks in TensorFlow is automatic differentiation. The idea here is that we have these basic operations and their derivatives, and we can create the graph with all the operations in parallel with the graph with all the derivatives. And so we can do this because we know each of these derivatives, and we can go through the whole computation graph and chain together all of these derivatives. So let's see an example here. Just to a quick overview here. You will have an optional tutorial this week where you'll see an example with dual numbers, how to do forward mode automatic differentiation. So basically, we are going through the computational graph for each variable and looking, as we do the computations, also looking at the derivatives and computing the derivatives in parallel. This is a simple method for automatic differentiation. That's why we put it in the tutorial. But it's not very efficient when you have lots of variables, because you need to run through the graph once for each variable that you have. And in deep neural networks, you have millions of variables, which are all the parameters that we need to update. So actually, what TensorFlow implements is reverse mode automatic differentiation, which is basically that algorithm we saw in backpropagation. We pass once forward, and we keep track of all the connections and all the intermediate values. And then we can go backwards through the graph and in parallel compute the derivatives for all the variables that we need, especially when they are all chained together in deeper and deeper layers. So this is what TensorFlow does. It's different from what you're going to see in the tutorial. In the tutorial it will be simpler. But the details are not what matters here. What's important is that you have an idea of how TensorFlow can solve all of these derivatives and compute them in order to train the network. So this is what we're going to see here. Imagine that we want to minimize this function, cosine of x. So we write in TensorFlow these operations. We have x, we compute the cosine, and now we want to minimize that. So basically, we have this computational graph. We get x, we get the cosine, and that is the result. But since we want to minimize this, we need the derivatives. And the derivative of the cosine with respect to x, in that case, is minus sine of x. And since this is known, this is also implemented, associated with the cosine function in TensorFlow. In parallel with this computational graph, TensorFlow will create this gradients graph, where you have the negative sign, the multiplication with the sine function, and so this is the derivative of that one. And TensorFlow keeps track of all the operations that you use, what are the corresponding derivatives, and creates that graph too. So this way it will have the gradient necessary to do the minimization. If you have something that is more complex, x squared, cosine of x, sine of x, then you still have all the gradients here. The product here for the x squared, the sine of x as the gradient of the cosine, and so on. So you have all of this graph representing the derivatives of all of those operations that you have there, so that then the minimization can occur, and in this case TensorFlow could adjust x to have the minimum value there. Okay, so going back to our simple model, we have these two parameters here. We want to classify this data set. So now what we can do, since we can compute the derivatives, we can start at some random point. So imagine that these coordinates here are the values for the two weights that we're trying to adjust. We start at some random point where the error is large, but we can compute at each example that we are presenting, we can compute in which direction to change our parameters so that we go down this error, this loss function. And during that, the parameters are changing, and eventually we get the best result that we can with this model. Which is not very good because this is just a linear classifier, but this shows how the derivatives are then used in stochastic gradient descent to solve this problem. This is stochastic because we are presenting examples at random, and it's gradient descent because at each point we compute the derivatives and we go towards the negative sign of the derivative, that is, we're going down the gradient of the function. Now, this is not a very good model for this case. We're going to see how to improve that. But first we're going to take a look on how we can use the gradient information to optimize our parameters. So one way of doing this is simply computing the gradient, that is the derivative with respect to all our different parameters, of our loss function. The loss function can be different loss functions depending on the problem. So you already saw the mean squared error as an example, logistic loss in logistic regression, for example, that's another one. But whatever loss function we use, we compute the gradient with respect to the parameters for some batch of examples. Typically, we use a group of examples because using one example at a time can be very inefficient. If you use several examples, since those matrix multiplications can be all parallelized, then it's easy to compute the contribution of all those examples in parallel at the same time, and only then update the weights of the network. So using batches can accelerate a lot this process. And we compute the gradient for a batch of examples, and now we're going to update all our parameters, the vector of parameters, by a small fraction of the corresponding gradient values for all of these parameters. So this is just a simple stochastic gradient descent algorithm. But we can improve this if we use momentum. So the idea is, instead of using the gradient just to keep doing these steps, we use the gradient information as an acceleration to change the velocity we had so far. And the velocity is given by the previous iteration. We start with the velocity 0, we use the gradient to increase the velocity, and then if we are going always on the same direction, these vectors will add and our velocity will increase. So by using momentum, by keeping this momentum going, we can greatly improve the efficiency of this minimization, especially when we are going in the same direction. So if you're going straight ahead, the velocity starts increasing, and so we jump a lot faster than if we don't use momentum. So if you use stochastic gradient descent, this basic optimizer, generally use momentum, it speeds up a lot the learning process, and makes a big difference here. There is a better version of momentum, which is to use the gradient as an acceleration to change the velocity, but by looking at the value of the gradient of the loss function when we move at the current velocity. So instead of looking at the parameters here, we first see how the gradient would look like after moving at this current velocity, and use that gradient to change the velocity. This is called Nesterov momentum, and the difference is basically here. Instead of evaluating the loss function at the parameters we are currently, we evaluate the loss function at the parameters we would be if the acceleration was 0 and we would just take another step. Now, this is very good for optimizing convex functions when you have a good idea of what the gradient actually is. But remember that in this case, in stochastic gradient descent, our estimate of the gradient is given by a small batch of randomly chosen examples. And this randomness messes up with the Nesterov momentum. So even though you can use this, there is this option in Keras. In practice, it doesn't seem to work particularly well because of the randomness in the stochastic gradient descent. So this is just an example between the comparison in this case between using standard momentum and Nesterov momentum, and you don't notice any difference between the two. Another thing that affects the performance of training, the speed of training, is the size of the MiniBatch. So basically, when we average over a set of examples, we get a slightly better estimate of what the true gradient is. Remember that the idea is to minimize the loss function on average for all possible examples. So if we use only one example, we don't have a very good estimate of that. If we use several examples, we get a better estimate of that. The main advantage, even though this is true, however, the main advantage is actually in computational speed. It's not so much the estimate of the gradient, but the fact that if you are using parallel processing, for example, GPU, you can easily compute tens or hundreds of examples at the same time without losing time because of that, and this will allow you to then take faster steps in training the network. There is one drawback in using large batches, which is that smaller mini batches tend to improve generalization and improve the final result because of the randomness they introduce. We don't get stuck in local minima. The search for better parameters is moving more randomly, and so can avoid these traps. In practice, what usually happens is that we use a mini-batch size as large as the memory allows, because note that when you feed in more examples at the same time into the network, all the tensors inside the network will increase in size because you are carrying all of those examples through the network. So usually the limiting factor is how much memory you have on the graphics card or something like that to take all of these examples. This is an example of comparing a mini batch of 10 and a mini batch of 1, and it looks to be the same because I'm plotting with the number of examples, not the number of mini batches. However, this is actually about 10 times faster if you are parallelizing the computations of those examples. So the trajectory is not very different, but the speed can be a lot greater if you use larger batches. Okay, so now let's improve the model a bit. We start with this very minimalistic pseudo neuron, but it actually is missing an important component, which is the bias. The reason I use this one is that it only has 2 weights, so it makes plotting the weight space a lot simpler. This one now has 3 weights, which are the 2 corresponding to the coordinates of the points we're trying to classify, and one that is, we can consider this to be a constant, 1, which is to make this weight independent of the data. So actually we have this multiplication of the inputs by these weights, and then this bias value, which is an independent value that we can adjust. And this is important because if we only use this model here, then if both coordinates are 0, what enters here will always be 0, and we have a 0.5 on the sigmoid. So actually this frontier here is sort of pinned here at the middle, at the center of the coordinates, I think somewhere around here, where we have 0, 0. It cannot move from there. If we have bias, then eventually, if it needs to, it can start to deviate because it has that additional value that can cause the frontier to shift. So it eventually moves a bit more to one side or the other as it needs. In this example, it doesn't move much because the data is centered, but eventually, if you look carefully, you can see some slight shifts. But the idea is that without this bias, you have everything pinned to the center of coordinates, because if the input is 0, then you can only have one output, which would be, for example, 0.5 on the sigmoid. So also we have a problem here, which is that one neuron cannot properly classify this data set. So let's add a few layers. We have this first hidden layer with a bias of 1, then we have another hidden layer here, and we can use these to do those transformations on the data. So now this would be the input, what the first layer is representing, what the second layer is representing, and then the final neuron is just cutting the representation of the third layer. So if we project this back to the input space by undoing those transformations, we see this frontier starting to curve here. So all of this we can do because we can set all of those operations in a graph. TensorFlow keeps track of all the derivatives and then applies those for training the network. Okay, so a few other details. The initialization of these weights, we are going to need to randomize the weights because we need to break the symmetry between the neurons. So you can imagine that if all the weights of neurons had the same value, they would all also have the same derivative, and they would all be updated in the same way. And so in fact all of those neurons would march in step and work as if they were just a single neuron with no difference between them. So the bias value can start, for example, at 0, it's not a problem, but the weights that we multiply by the inputs need to be different from neuron to neuron. So we use random initialization for these weights. I'm going to talk a bit more about this in a few weeks, but the idea here is that not only it's random, but it should be close to 0, where the activation functions have a higher gradient in this case, and also to avoid, when we are stacking all of those transformations, to avoid the problem of going into numbers that are too large and getting some overflows. Since we initialize the weights at random, when we run the same network, train the same network on the same data different times, since the weights are initialized at random and the examples are presented at random, we can have different trajectories. So sometimes the network learns what we want earlier, other times it can take longer. So remember that this is not deterministic, so it may vary a bit from run to run. Another important thing is to standardize the inputs. If we have different features at different scales, yes?
for the slide before. So is that the error on the y-axis?
Yes, this would be the error. This is just an example with a mean squared error. So if you take the square of 0.5, that's 0.25. This here is just at random.
Two times it doesn't like converge to a zero error at all, like those two.
Yes. For this example, I used a high learning rate. There is some instability there. You can see here it fluctuates a bit, but it may eventually converge. It may just take a longer time here. We'll see some of these details also of fine-tuning these parameters in a few weeks. But the idea here is just that this is a bit exaggerated, but in general, you cannot rely on having exactly the same results when you run again, because there are many random factors here. Yes.
How can I understand the learning rate actually? So I understand that if you have a high learning rate, it doesn't work as good, but how?
Well, we're going to see those things in more detail after you experiment a bit, but basically, if it takes very long to start learning, you may experiment increasing the learning rate. If you start having oscillations like this, then the learning rate may be too high and you cannot find the optimal points because you overshoot when you go in that direction. So the learning rate is the size of the step, and if you take steps that are too large, you may pass over the lowest points and never find those best points. But you can see that if you see some oscillations and things start behaving erratically in these plots. So this is also important, standardization, because if we are using the same learning rate for all the different weights of the neurons, if some weights are being used on features that have a smaller scale and others on features that have a larger scale, then the learning rate may actually be too large for some features and too small for others, and everything will be out of balance. So one good idea is to use standardization on the data that we are feeding into the network in order to have all the ranges, the standard deviation in all the features to be the same, and also have everything centered at zero. This is also good if you are doing regression problems, try to do a regression. You may also do this on the output in order to help you have always the same intuition about what would be a large error or a small error, because if you are dealing with things that have different scales, this may mess things up a bit, especially if you're doing regression to several values, because the different scales will give more weight to some of them than others. So remember these points, that if you have things that are at a larger scale than others, if you don't rescale everything evenly, those will weigh more on the all the multiplications that you do here, on the gradients, on the loss function, and so forth. So what we call one epoch during training is one pass through the whole training set, and this batch or mini-batch will be the selection of training examples we are presenting to the network to compute the gradients and then update the weights. So typically we have a large data set. We use relatively small numbers for the batches. We pass all these batches through the network by first randomly ordering the training set and then picking each example once in the batch. After we pass through all the examples in the training data, we repeat this. We reshuffle everything and we repeat the process. So each pass will be one epoch, and generally you need several epochs or many epochs to train the network. If you have a very large data set, then and if there is a lot of redundancy in the data set, you may need fewer epochs, because when you pass through the data set, the network has already seen many times the same kind of examples. But if you have a smaller data set, you may need many epochs before the network learns. it's important to shuffle the data in each epoch, otherwise you can have this kind of effects, because if you're always passing the examples in the same order, you may be going back and forth as you are looking at different shapes of the loss function for each of the different batches that you are presenting. The learning rate, there is this problem. We're going to see this in more detail, but basically, as I said, if it's too small, it can take too long. If it's too large, it can start to oscillate as you miss the lowest points in your loss function. Okay, so to sum up this first part, deep down in the training of the network, we have all of these matrix operations, and if you want to implement these networks at the lower level, that's what you use for simulating all of the neurons. And then with all of these elementary operations that we have, TensorFlow also includes the derivatives for all of the operations. So when you build the graph with a series of operations, TensorFlow also builds the graph with the derivatives, and that is what allows it to compute the gradients, because it will do this automatic differentiation by following the other graph too. We saw this more detailed example of how to train these different layers, these transformations, and the multi-layer perceptron which I use here is a special case where you have all the different layers and they are fully connected and the data is only going forwards. We're going to look at this case in these first lectures because it's the simplest one and easiest to understand. But these same principles apply to other architectures like convolution networks, recurrent networks, and so on, which we're going to see later on. It's the same idea. You have a series of operations, elementary operations, you have all the derivatives associated with them, and TensorFlow keeps track of all of the necessary computations to be able to calculate the derivatives. So there are some reviews on algebra and calculus in these chapters of Goodfellow's book, and a bit about optimization on chapter 8.